Hi, this is John Whitaker, and this is going to be the 8th video lecture for analysis. And today I'm going to start off with a definition. It's a very lengthy definition about a vector space. So here's the definition. We start off with letting F be a field and V be a set. Then V is a vector space over F if there are two binary operations, addition and scalar multiplication, such that for all U, V, and W in the set V and scalars, they're called A and B, that are in the field F, we have a bunch of properties. 10 properties. So the first one is that if you take two, they're called vectors, two guys in V, and you add them together, you get something that's in V. Second one, if you take U plus V, that's the same thing as V plus U. The commutativity occurs. Associativity occurs as well. That is, that if you take U plus V, add that to W, that's the same thing as U plus whatever V added to W is. Fourthly, there exists a zero element of V such that if you take a vector U and add that zero to it, you just get U. So that is the additive identity. 5, for each V, let's say U, in the set V, there exists a minus U in V such that U plus minus U equals to the zero vector. Sixthly, if you take a scalar times object in V, that's going to be an object in V. 7, if you have a scalar, something from the field, times U plus V, that's going to be equal to the scalar times the first vector plus the scalar times the second vector. So it's the distributive property for the scalars involved. The 8th property is if you take two scalars, add them together, and then multiply them by a vector, that's the same thing as the first scalar times the vector plus the second scalar times the vector. Ninth property, if you take a scalar times a scalar that's been multiplied by a vector, that's the same thing as the two scalars multiplied together and then times the vector. And then finally, since F is a field that has this element 1, and if you multiply that by a vector u, you just get the vector u with the scalar multiplication. So that's what it means to be a vector space over a field. You satisfy your set that satisfy these 10 properties. What I want to list now is another definition, and it says for each positive integer k, let Rk be the set of all ordered k tuples, I call them x bar equal to x of 1, comma, x of 2, comma, all the way up to x of k, where x of 1, x of 2, all the way up to x of k, each one of them is a real number. That's not all, we're almost done. And they're called the coordinates of x bar. So that's what our k is. Now, if we let x bar equal to x1, x2, all the way up to xk be in Rk. So each one of these coordinates is real numbers. And we let y be equal to y1, y2, up to yk, the elements of Rk. Then we can define, and let alpha be element of R. Then, on Rk, define addition by x bar plus y bar equal to, you add each coordinate together, so it's x1 plus y1, comma, x2 plus y2, comma, all the way up to xk plus yk. And scalar multiplication scalar multiplication. Okay, so here you take alpha, some real number, times x bar. That's going to be equal to alpha times x1, x2, all up to xk, that tuple, and it's going to be defined as the k tuple, which is alpha x1, comma, alpha x2, comma, all the way up to alpha xk. So that's what we're defining, these two operations on Rk. And so let's look at some examples of this. So examples in R4 might include that if we have, first thing for the scalar multiplication, if we had 6 times, let's say minus 6 times minus 1, 1/5, 3, and 7. Okay, so this is a scalar times something, a vector in R4, object in R4. What we get here is 6 minus 6/5 minus 18 and minus 42 is the outcome. And then the second example, if we had 3 minus 2, 4, and 7, that is an object in R4, plus another object in R4, minus 1, 5, 6, minus 13, then an answer, when we add these, we add each coordinate together, so 3 plus minus 1, that's 2, that's 3, that's 10, and finally that's minus 6 would be the answer. As a fact, RK is a vector space over the field R with the 0 vector being equal to 0, 0, all the way up to the last entry, where there's k entries being 0, and minus x bar will be equal to minus x1, minus x2, all the way up to minus xk, where x bar is equal to x1, x2, all the way up to xk. So RK is a vector space. To show RK is a vector space, I'd have to show that RK satisfies those 10 vector space properties. I'm not going to do that. So we will not show that RK is a vector space in its entirety. But we will look at a few properties, okay? But note, if I took x bar plus y bar, which would be equal to, let me write here, x1, x2, up to xk, plus y1, y2, up to yk, and add them together, I get x1 plus y1, comma, x2 plus y2, comma, and then xk plus yk eventually. And this would be in RK, and the reason it would be in RK is that there are k number of entries, k number of coordinates, and each coordinate is a real number. Okay, because if you add two real numbers together, you get a real number. So that would show the first identity. And you could also say, well, this is equal to y1 plus x1, not the first identity, first property. And this is also equal to y2 plus x2, all the way up to yk plus xk. And if you wanted, you could say, well, that's the same thing as y bar plus x bar, and that would show that x plus y is equal to y plus x, showing the commutativity for the addition, which was another property. we needed to show. And just to show one more identity involving scalars, one more property involving scalars that would need to be shown for proving that RK is a vector space. Look at one more thing. Alpha plus beta times x bar would be equal to alpha plus beta, where they are real numbers, alpha and beta are real numbers, times x1, x2, x3, all the way up to xk. And then the way that we do this multiplication is we take the scalar times each one of the coordinates. So I get alpha plus beta, x1, comma, alpha plus beta, x2, and we continue on all the way up to alpha plus beta times xk. And here, because this is a field, we have the distributive property for the real numbers. This will be alpha x1 plus beta x1, alpha x2 plus beta x2, all the way up to alpha xk plus beta xk, in the last coordinate. And then this can be broken into alpha x1, comma, alpha x2, comma, all the way up to alpha xk plus the vector that is beta x1, beta x2, all the way up to beta xk. And then you could factor out an alpha, x1, x2, up to xk, and factor out the next vector, a beta, x1, x2, all the way up to xk. Because of the way scalar multiplication is defined, I can go from this step to this one. And then this is equal to alpha x plus beta x, which was one of the properties for a scalar, for a vector field that needed to be shown for RK to be a vector space. Okay, so RK is a vector space. But now we're going to put define a certain quantity on this called an inner product. So an inner product on RK, we're going to work on. As a definition, given x bar and y bar being an element of RK, then the inner product between x bar and y bar is denoted by these square brackets, angular brackets here, x bar, comma, y bar, and given by, okay, so the inner product between x and y, where x and y are in RK, is equal to the sum of x, let's say j times yj, these are the coordinates, as j runs from 1 to k. That's its definition. Let's look at an example. So if we let x bar be equal to minus 1, 2, minus 3, and 0, and y bar be equal to 4, minus 2, minus 3, and 5, then the inner product between x and y would be equal to, well, it would be, you take the first coordinates and multiply them together, so it's minus 1 times 4, and you add that to the second coordinates multiplied together, it's 2 times minus 2, and then you take the third coordinates and multiply them together, minus 3 times minus 3, and then finally you have the fourth coordinate, 0 times 5, multiplied together. And so what you get here, I think I have just enough room here. This is minus 4 plus minus 4 plus 9 plus 0, and so that ends up being 1. So that's an example of an inner product in RK, in R4 in particular. As a definition, now we're going to find the norm, so we're going to let x bar be an element of RK, then the norm of x bar is denoted by x bar in double bars, in double lines here, and given by x bar is going to be equal to, it's going to be the sum as j runs from 1 to k of x of j to b squared, and then you take the square root of that. And that is the same thing as the inner product with x bar with itself, okay, raised to the 1/2 power, okay, where x bar is equal to x1, x2, all the way up to xk. That's the definition of a norm. We give a fancy name for RK with this inner product and this norm, and I'm going to write that up next. So as a definition, the vector space RK with the previously defined inner product and norm is called Euclidean K-space. I'm not going to go into this very much, but the inner product gives some kind of angle of representation between vectors, whereas the norm gives the distance between vectors, if you will. And so we're going to now do some properties about inner products. Okay? So here's the theorem. It says, suppose x bar, y bar, and z bar are elements of RK, and alpha is an element of R, so that's a scalar. Then, here's what we have. First of all, the norm of x bar is going to be greater than or equal to 0. And another property is the norm will be equal to 0 if and only if x bar is 0. C, the norm of alpha times x is equal to the absolute value of alpha times the norm of x. D, turns out that the norm of x minus y, x times y, is less than or equal to the norm of x times the norm of y. I'd like to think about that for a second. E, x plus y, and I'm going to have to go back to D for a second, is less than or equal to the norm of x plus the norm of y. And F, the norm of x minus z, is less than or equal to the norm of x minus y plus the norm of y minus z. I'm not sure that got into the board very well. Let me turn it, and while I turn the camera just a little bit, so you can see it a little better, let me look up part D for a second. Give me a sec longer. Okay, I didn't write this down as well as I would like to. There was something that was bothering me about D. And here's what it should say. So it should be, I believe, the absolute value of the inner product of x with y is going to be less than or equal to the inner product, the norm of x times the norm of y. That's what it should have said. Sorry, so I had something incorrect. Okay, we want to prove these. Really, what I had listed was relatively okay. Just in terms of notation here, something that I failed to mention is that often we say x dotted with y is equal to the inner product between x and y. And so with that, if I had written previously, remember, this should be common here. X dotted with y, the absolute value of that would be less than the norm of x times the norm of y. And that would have been accurate. I'm sorry. Okay, we want to prove these facts. Okay, so here's what we're going to do. We're going to let x bar, y bar, and z bar be elements of RK, and alpha be an element of R. So for part A, we want to show that the norm of x is greater than 0. So the norm of x, what that's equal to, we'll show it's greater than or equal to 0. What that's equal to, it's the sum of j running from 1 to k here of x sub j squared, and you're going to raise this to the 1/2 power. So that's what it is. And now, since x of j is an element of R, then x of j squared is going to be greater than or equal to 0. So the sum, as j runs from 1 to k, of x of j squared is going to be greater than or equal to 0. So we can take the square root of it, and it's going to be non-negative. Where I didn't write this out so well, but the x bar is defined to be x1, x2, all the way up to xk. And that proves part A. Let's make this conclusionary statement. So the norm of x is greater than or equal to 0. Then part B, we want to show that the norm of x equals to 0 if and only if x equals to 0. And so here's the proof in this direction. So it's if and then only if statement, so we're going to have two parts to this proof. So here we're going to suppose the norm of x equals to 0. Okay? That means that the sum as j runs from 1 to k of x of j squared raised to the 1/2 power equals to 0. If you square both sides, you get that sum is going to be equal to 0. Okay, and what that means is, so for each j, okay, x of j has to be equal to 0. For if not, then x of j squared will be greater than 0, and that will make the sum, as j runs from 1 to k of x of j squared, be greater than 0. Okay? Be greater than 0. We don't have that. And then going in this direction, suppose x bar equals to 0, which is equal to 0, 0, every entry, every coordinate 0. Then we talk about the norm of x. That's going to be equal to the sum as j runs from 1 to k of 0 squared. So each coordinate 0 you'll be squaring them, and that's just 0. Part C, we want to show that the norm of alpha times x bar is equal to the absolute value of alpha times the norm of x bar. So note the norm of alpha times x bar will be equal to the norm of alpha times x1, x2, all the way up to xk, which equals to the norm of alpha x1, this vector, alpha x2, up to alpha xk. That's what that is. And so if we apply the definition of what the norm is, remember this is going to be raised to the 1/2 power here. I forgot to write that down. What I wrote was correct, but I want to include the one step for what the norm is.
Okay.
So that's equal to, it's going to be the sum as j runs from 1 to k. So this norm is going to be each coordinate. So alpha times x sub j is each coordinate. You have to square that and take the square root of it, so raised to the 1/2 power. And this is equal to, you can rewrite this as the sum as j runs from 1 to k of alpha squared x sub j squared, okay, raised to the 1/2 power. And then the alpha squared doesn't have anything to do with index j, so it's a constant with this sum. It can be pulled out. Alpha squared times the sum as j runs from 1 to k of x sub j squared, and all that raised to the 1/2 power. That's the same thing. The 1/2 power is the square root. So the same thing as the square root of alpha squared times the square root, or if you will, the sum as j runs from 1 to k of x sub j to be squared raised to the 1/2 power. The square root of a real number being squared is its absolute value. So that's the absolute value of alpha. And this quantity, this sum of the coordinates being squared raised to the 1/2 power, that's the norm of x. So that proves that fact. Okay, so for part D, we want to show that the inner product between x and y inside absolute values is going to be less than or equal to the norm of x times the norm of y. That's what we're going to show. And so we start off here with the absolute value of this inner product. Now, x is that k tuple, x sub 1, x sub 2, all the way up to x sub k, and y is that k tuple, y sub 1, comma, y sub 2, all the way up to y sub k. We do the inner product between the two. So we have the absolute value. This is going to be the sum as j runs from 1 to k of its x sub j times y sub j. Okay, that's what we have. So that's something to keep track of. So we'll stop there for a second. Now, if we look at the norm of x, that's going to be equal to the sum as x runs from 1 to k of x, as j runs from 1 to k, of x sub j squared all raised to the 1/2 power. And similarly, if you look at the norm of y, that's going to be equal to the sum as j runs from 1 to k of yj squared raised to the 1/2 power. Okay. Okay. So there's something that we should take an observation of, and that is that we should note for a real number, A, if we think of it as also being a complex number, A conjugate is equal to A, because it doesn't have an imaginary part, its imaginary part is 0. So by the Schwarz inequality, so we're thinking about complex numbers for a second, by the Schwarz inequality, the sum as j runs from 1 to k of xj, yj conjugate inside the absolute values, b squared, is going to be less than or equal to the sum as j runs from 1 to k of the xj's inside absolute values to b squared times, okay, the sum as j runs from 1 to k of the absolute values of the y sub j to b squared, the modulus here. And that's what we have. Close to being done. But for real numbers, the modulus of xi squared is going to be equal to the square root of xi, this was j here, xj squared to b squared, so that's what the modulus is. And that's just going to be equal to xj squared. Okay. So what we have then is the absolute value of the sum as j runs from 1 to k of xj times yj. This was y conjugate, y sub j conjugate, but that's the same thing as y sub j because it's real. Inside absolute values to b squared is less than or equal to, rewriting what we have from the Schwarz inequality, this would be the sum as j runs from 1 to k of the xj squared, okay, times the sum as j runs from 1 to k of yj squared. This is nothing more since, first of all, since each side is positive real numbers, is a positive real number, applying the square root function to both sides, we have, okay, this would say, so you take the square root of this, the square root and the square would cancel with each other because this is positive. So you have the sum as j runs from 1 to k of xj, yj is going to be less than or equal to. Here you take the square root of this guy, so it would be the sum as j runs from 1 to k of x of j squared, all raised to the 1/2 power, times this sum here is j runs from 1 to k of y sub j b squared, be raised to the 1/2 power. And so what that gives us is that other side is nothing more than, so here, I forgot the absolute values about this, okay? So the square root and the square cancel, we still have absolute values. So this is the inner product between x and y, inside absolute values, would be, well, let's write it over here. It gives us the conclusion we want. So what that says is that left-hand side was the absolute value of the inner product between x and y. It's going to be less than or equal to, and the first statement here was nothing more than the norm of x times the norm of y. That proves it. Okay. The next thing that we want to show is we want to show, this is part E, that the norm of x plus y is going to be less than or equal to the norm of x plus the norm of y. So here's what we start off with. We know that the norm of x plus y to be squared is nothing more than the inner product of x plus y with itself because remember the norm of a vector was equal to the inner product of that vector with itself raised to the 1/2 power. So this is equal to the sum, so this inner product is the sum of the x, so j runs from 1 to k, of x sub j plus y sub j, that's what this would be, to be squared. The inner product behind the b. And this is going to be equal to the sum as j runs from 1 to k. This is x sub j squared plus 2x sub j, y sub j plus y sub j squared. That's what we have. You can break this up into 3 sums. So it's the sum as j runs from 1 to k of x sub j squared plus, I'll pull out a 2, and it's the sum as j runs from 1 to k of x sub j, y sub j, plus, here, this is going to be the sum as j runs from 1 to k of y sub j squared. Okay. So this is equal to the norm of x bar to b squared plus, this is 2 times, that sum that we had before was the inner product between x and y, plus, here this is going to be the norm of y to b squared. Now, it turns out that this inner product is a real number, and so what we're going to get in replacement of it is its absolute value is going to be bigger than it. So I'm going to replace this, so this will be less than or equal to the absolute value of the inner product between x and y plus the norm of y to be squared. And then this is going to be less than or equal to, now here I've got squared, the norm of x to be squared plus, by the previous problem, this can be replaced by the norm of x plus the norm of y, and it gets bigger, plus the norm of y to b squared. And then this is equal to the norm of x plus the norm of y, its factors, to b squared. So what we've just shown is that the norm of x plus y to b squared is less than or equal to the norm of x plus the norm of y to b squared. And since both of the objects being squared are greater than or equal to 0, applying the square root to both sides will hold the inequality, and it will have the norm of x plus y is less than or equal to the norm of x plus the norm of y. And ends that part of the proof. There's only one more part of the proof to do, so let's go ahead and do it. It's short, and then we'll call it quits. Okay. So here, the part F, we want to show that the norm of x minus z is less than or equal to the norm of x minus y plus the norm of y minus z. That's what we'll show. Okay. So here, note that the norm of x minus z is the same thing as the norm of x plus, well, let's make it minus y, plus y minus z. So all I did was add and subtract y. Okay? And now we think of this as one quantity and y minus z is another quantity. They're being added together and got the norm inside them. And so by the previous fact, this is less than or equal to the first guy, so which is x bar minus y bar, plus y bar minus z bar. And that's what we wanted to show. So that proves it. Ladies and gentlemen, that's enough for today. Thank you very much.